Okay, so today we need to talk about pressure again. That should be a pretty short presentation, but basically we need to talk about the different types of pressure that we commonly run across. Two of the types of pressure that we're going to run across in PSI is going to be gauge and absolute pressure. So what is gauge pressure? Gauge pressure is a pressure that ignores the fact that we have atmospheric pressure all around us. Well, basically, when we're sitting in our classroom, when we're walking outside, we are experiencing a pressure at all times. And that pressure is atmospheric pressure. So, OSPHERIC, pressure is going to be equal to 14.7 psi. So, if we have 14.7 psi, why don't our gauges read 14.7 psi whenever there's no pressure on it? Because they're gauge pressures. They are ignoring the atmospheric pressure. As you can see here, this is a different pressure gauge. And it's actually what we call an absolute pressure gauge, and it's reading the absolute pressure. So when there is no pressure at all on this gauge, it's going to read 14.7 psi. Just because it's setting on, and I say no pressure at all, I'm saying when it's in the atmosphere, when it's on Earth, but there's no pressure other than atmosphere, then it's just going to read 14.7, whereas our gauge pressure is going to read 0. Basically, just to get between the two, all you're going to do is either add or subtract 14.7 to get from atmosphere from a absolute pressure, okay, which is to a gauge pressure. You're just going to subtract 14.7 to get from a gauge pressure to an atmospheric pressure. Or a absolute pressure. You're going to add 14.7. That's pretty much all there is to it. But we do need to talk about one other thing, and that's the idea of a vacuum. So let's just say, for example, that we have atmospheric pressure here. Okay, this is atmospheric pressure. Here we have some other pressure. Let's say that this is this differential here is something like let's say 9.7 psi, and we need to find this differential, but right here is absolute zero pressure, and this is atmospheric pressure. Which means this right here has to be 14.7, right? So what is this pressure right here? Well, if we take 14.7 minus 9.7, we should get 5 psi. So the question is, let's just call this this pressure right here. We'll call this pressure A. All right. Well, let's not use A. There's a lot of A's already. I'm gonna call this pressure Z. So what is Z in terms of absolute pressure? Well, we're just looking for the difference here between absolute pressure and our Z pressure. So Z is equal to 5 psi, and to denote it, and it's an absolute pressure, we're going to say A, psi A. But what is it in gauge pressure? Remember, gauge pressure ignores atmospheric pressure. So we have some pressure that's below atmospheric pressure. Well, if it's below, then in gauge pressure, it's got to be negative, okay? So what is it? It's negative 9.7. So Z would be equal to negative 9.7 psig. So again, to get from psig to psia, all we got to do is add 14.7. And to get from psia to get psig, we subtract 14.7. And you can see that that's the case here. So absolute and gauge pressures. Now, when we say a vacuum, I just want to specify that a vacuum is just any pressure that's below atmospheric pressure. There is a little bit more to a vacuum, but we're not. That's all we really care about right now. But there are other units of pressure, and we've already talked about psi. We've used pounds per foot squared as well, pounds per inches squared. We've talked a little bit about the SI unit. We're going to talk about that more in a second. But another way of measuring the pressure is to measure the height of mercury. Now, the interesting thing is this is the way pressure used to be measured. We don't use that anymore, but if we look at here, this is something. This would be a vacuum or absolute. I'm gonna say instead of saying a vacuum because that's sort of it's not very specific. I'm gonna say 0 psia. So basically an absolute vacuum. Okay. We have over here the atmosphere pushing down on the mercury, okay? And because of that, mercury is actually going to go up into the tube some height above the fluid level, okay? So there's some height here, right? And we can figure out that height using our pressure equals specific weight times height. And this would be the specific weight of mercury. Which is 846.14 pounds per foot cubed. So if you figure out what is 14.7 psi, and then you convert psi to psf, and then use your specific weight and figure out what the height of mercury under 14.7 psi, you would find that there are 29.92 inches of mercury and 14.7 psi. So that's your conversion ratio. So you don't have to know the specific weight of mercury to do that conversion. Hopefully you'll never run across inches of mercury, but I do want to go ahead and talk about that for a second. We also have atmospheres or bars. So 1 bar equals 1 atmosphere equals 14.7 psi equals 101 kilopascals. Pretty easy. Bar is a very common pressure. It's used around basically around the world. If you are not talking about kilopascals, you're much more likely to come across bar or an atmosphere than you are psi, to be honest. But that is another common pressure, and here are your conversion ratios. Okay, so aluminum has a density of 27 grams per centimeter cubed. Find the density of aluminum, the specific weight of aluminum, and the pressure in psig at the bottom of a molten pot of aluminum with a fluid height of 13.5 feet. So let's do this conversion real quick to get to proper slug per foot cubed. We have 20. I'm sorry. We have. I'm going to start up here. 2.7 grams per 1 centimeter cubed. 1 kilogram is 1,000 grams. Grams cancel. 1 slug is 14.59 kilogram. Kilograms cancel. 1 million centimeters cubed equals 1 meter cubed. meters cubed cancel. 1 meter cubed equals 35.28 feet cubed. So we get 5.24 slug per foot cubed. We want to find the specific weight. So to get specific weight, we're going to times by 32.2 feet per second squared. And I'm going to go to the next slide for no reason at all. Let's go back. And we're going to get a specific weight of 168.72 pounds force per foot cubed. So we found the density and specific weight. So here was the density. Here's the specific weight. So now the next thing to do is to find the pressure and PSIG at the bottom of a pot of molten aluminum with a height of 13.5 feet. So we have pressure equals specific weight times height. So we have 168.72 pounds force per foot cubed, and we're going to times this by 13.5 feet. We get a answer of 2,277.72 pounds force per foot squared. Of course, then we have to 1 foot squared divided by 144 inches squared equals 15.81 PSIG. So there is our final answer there. And that, of course, wrote right over top of my 15. There we go. So, next question. A hydraulic reservoir has an outlet 2 inches from the bottom of a with a fluid height of 18 inches. Has an outlet 2 inches from the bottom and a fluid height of 18 inches from the bottom. The hydraulic fluid being used has a specific gravity of 0.8. Find the following. Alright, so first of all, let's explain this for a second, because I read that wrong at first, but it's pretty easy. Let's say we have an outlet here, and that would be 2 inches. This height right here is 2 inches. Then we have a fluid height, and it has a height from the bottom of 18 inches, which means that our differential from here, from the outlet to the fluid height, is going to be 16 inches. So find the pressure at the outlet in PSIG, find it in PSIA, and find the pressure in the outlet in bar, and then we're going to find the pressure in PSI. It should be PSIA. So PSIA. The first thing to do is to find the pressure at the outlet in PSIG, which shouldn't be too hard. We have our pressure equals specific weight times height. We do need to find the specific weight of this fluid. So the specific weight or specific gravity is 0.8. So specific gravity of the fluid is equal to 0.8. Okay. Of course, we know that specific gravity equals the specific weight of the fluid divided by the specific weight of H2O. And the specific weight of H2O is 62.4 pounds force per feet cubed. So all we have to do is take 62.4 times 0.8, and so to do that, so specifically the fluid equals 62.4 pounds per foot cubed times 0.8 equals 49.92 pounds force per foot cubed. Of course, then we need to times that by the height because we want to find the pressure. And so the height is going to be at the outlet 16 inches. So let's do that conversion real quick. So we're 16 inches times 12 inches is 1 foot. And see what, let's do this a little differently. I was just looking at my notes, and that's not the way I did my notes. So we're going to actually convert this up here into pounds per inches cubed. So we'll do that. This is a little different, so it's good. 1 foot cubed is 1728 inches cubed. And that's going to give us 0.028 repeating pounds force per inches cubed. And then of course we can times this by 16 inches and we get, and it's probably actually the better way of doing it now that I see that, 0.462 PSI, and of course this is G. Okay, so there we have that one. Let's go ahead and find this in PSIA. So to find it in PSIA, 0.462 PSIG, we're going to add 14.7 PSI. PSI, just regular PSI. Apparently that doesn't erase. There we go. PSI, and that's going to give us 15.162 PSIA, 0.462 PSIG, and we're going to times this by, to get bar, 1 bar equals 14.7 PSI. That's going to give us 0.03144 bar. So there's that, and there is that. Oh, that was right. I just realized. Find the pressure at the bottom. So let's take this 0.028 pounds force per inches cubed, and then we're going to multiply that by 18 inches instead of 16 because of this right here. And that's going to give us 0.52 PSIG. Alright, that is that one done. Alright, hopefully you understand a little bit more about pressure, absolute pressure, gauge pressure, bar, inches of mercury. If you have any questions, let me know.